You know, in math, this whole idea of nothing is actually surprisingly tricky. So today, we're going to demystify the most fundamental types of sets you'll ever run into, all the way from a set with absolutely nothing in it to a set that contains, well, everything. Let's dive in.
All right, let's get right to it. Here's the big question, the one that trips so many people up and costs them easy marks on exams. Is the number 0 the same thing as the empty set? The short answer? No, not even close. And by the end of this, you're going to know exactly why.
Okay, so let's start with this whole idea of nothingness. In mathematics, we have to be super precise about what we mean when we say nothing, and that's where our very first concept comes into play.
First up, we've got the empty set. You might also hear it called the null set, and it's exactly what it sounds like, a set with 0 elements inside. Nothing. You can write it with that special symbol, phi, or you can just use a pair of empty curly braces. Now, to make this crystal clear, we're going to use a really simple analogy. I want you to think of every set as a bag. Got it? So what's an empty set? It's just an empty bag. Simple, right? This little analogy, I promise you, is the key to dodging all the common mistakes.
And yeah, speaking of mistakes, let's talk about the traps. The ones that professors absolutely love to put on exams. This is where our little bag analogy is about to become your best friend. So let's circle back to that first question. Is the empty set the same as the set containing the number 0? Using our analogy, this becomes so obvious. The empty set, phi, is an empty bag. The set 0 is a bag with the number 0 sitting inside it. They are obviously not the same thing. One is empty, the other has something in it.
Okay, now let's take this trap to the next level. This is the one that really gets people. What about the set phi? Is that set empty? No way! Think about it with our analogy. It's a bag, and inside that bag is one item. And what is that one item? It just happens to be another empty bag. So the outer bag is not empty. It has something inside it.
All right, we've handled nothingness. Now let's move on to sets that actually have stuff in them and see how we classify them based on, how much stuff that is.
So a finite set is basically any set where you could, in theory, count all the elements and eventually get to the end. The set of letters in the alphabet? Finite. The set of people in your family? Finite. There's a definite end to the list.
But what if the elements just go on and on and on, forever? Well, then we call it an infinite set. The classic example is the set of natural numbers, 1, 2, 3, and so on. We use those 3 little dots, the ellipsis, to show that this list never, ever stops.
And hey, here's a quick pro tip for you. Next time you're in an exam and you see those 3 dots, just take a second, pause. Ask yourself, is this really infinite? Or did the question mention a limit somewhere? It's a fantastic little mental check that can save you a lot of trouble.
Next up is a singleton set, which is honestly just as simple as it sounds. It's a set with, you guessed it, a single element. The set with just the number 5 in it, that's a singleton set. And our tricky little set from before, phi, that's also a singleton set.
So what makes 2 sets equal? The rule is simple. They have to have the exact same elements inside. And this brings us to a golden rule of set theory. Order does not matter at all. The set ABC is exactly the same as the set CBA. As long as the members are the same, the sets are identical twins.
We've gone from nothing all the way to infinity. Now let's talk about the biggest set of them all, the one that contains everything, at least for the problem you're trying to solve.
This is called the universal set, and we usually show it with a capital U. Just think of it as the boundary, or the universe for your specific math problem. All the other sets and elements you're talking about have to live inside this one big box.
For example, if your problem is all about students at a certain university, then the universal set would be all the registered students there. If you're talking about even numbers, your universal set is probably all the integers. It just sets the context for what you're doing.
Okay, before we wrap this up, I want to leave you with a clever little trick. It's going to tie together everything we just talked about with the empty set perfectly.
First, let's learn this fancy word, cardinality. It sounds complicated, but it's not. It's just the math way of asking, hey, how many things are in this set? We write it as NA, which just means the number of elements in set A.
So, let's apply this. What is the cardinality of the empty set? In other words, how many things are in an empty bag?
The answer is, of course, 0. An empty bag has 0 items. The number of elements in the empty set is 0. Simple enough, right? But here's the punchline. What is the cardinality of the set containing the empty set?
How many things are in the bag that has an empty bag inside of it?
The answer is 1. Because there is exactly one thing inside that set, and that one thing is the empty set itself. This one little question perfectly proves that phi and phi set are fundamentally different concepts.
So there you have it. You've mastered the difference between an empty set and a set that contains emptiness. But this is just the beginning. Next time, we're going to go deep into subsets and power sets, and trust me, that's where things get really fascinating. I'll see you then.